Hello and welcome to our introduction to vectors. A vector is a geometric object that has magnitude, which is length, and direction. A scalar is just a number in real numbers, which has no direction, only magnitude. Familiar examples of vectors are force, velocity, acceleration, pressure, flux, and so on. A vector can be represented geometrically by an arrow, AB, which starts at the initial point A. We typically show A with X sub I and Y sub I for initial, and a terminal point B with X sub T, Y sub T components for T, and T stands for terminal point. Now, with initial point and terminal point, I can tell how much rise and run this vector has, and that's the difference between X terminal Y and Y X initial is going to be the run, and Y terminal minus Y initial is going to be the rise. Those are the two components of this vector. This vector is in 2 dimensions. Now, the nice thing about the vectors is that translating a vector does not change it. The magnitude and direction remains the same. So this was the first position. Now I'm moving it, and I like origin. Now the vector starts at origin, and the notation that I use for the vector, which was the components were the difference between X terminal and Y and X initial, and then Y terminal and Y initial. And then there were brackets that were angled. This notation, the components of this are the same as the components of the endpoints if it starts at origin. Again, notation, we typically show vector with V with an arrow on top. And then if we are emphasizing the initial and endpoint, we use AB with an arrow on top. This was the 2D situation, 2-dimensional. Now in 3-dimensional, you also have an arrow. It starts at a point A, which is the initial point. A has 3 components, xi, yi, and zi. And then it ends at a point B. The B has 3 points, xt, yt, zt, x terminal, y terminal, z terminal. Now, basically the horizontal in x direction, y direction, and then in z direction that this vector traveling is done by finding the difference between the components of the terminal point and initial point. So again, we have 3 components because it's 3D. X sub t minus yi, first component, y sub t minus yi, second, z sub t minus zi is the third component. We put this in brackets that are angled again to show it's a vector. And then the other presentation is AB with a vector on top. Again, I can translate this and take it to origin. You guessed it. And again, the presentation that I showed you before also has the same component as the terminal components of this vector if it starts at origin. Magnitude of a vector. The magnitude or length of a vector, V, is the distance between its initial point and terminal points. So if I have a vector represented by components A and B, basically, I can imagine that the initial point is 0 and 0, and the terminal point is A and B. Then the distance of the point A and B from origin is square root of A squared plus B squared. If the vector, let's say W, has 3 components, A, B, and C, then the distance of the terminal point from origin is going to be square root of A squared plus B squared plus C squared. And this is exactly the magnitude of V. This one is the magnitude of W. Now imagine in 2D. Here's a vector, drop down a perpendicular to the horizon. So I drop down a perpendicular to horizontal. And then you can see that the rise and run of the vector, the horizontal and vertical components of the vector form a right triangle. Therefore, the hypotenuse of this right triangle by Pythagorean theorem is going to have length square root of rise squared plus run squared. So that's explaining the distance formula. And here with X and Y axis in there, it's easier to see that run is X component and rise is the Y component. Example, let's say V is vector 8 and 3. What is the magnitude of the vector V? So you have to take square root of first component to power 2 plus second power component to power 2 quantity. And that's square root of 73. Three-dimensional. Let's say V with a B and vector on top means the vector from A to B with A equal to x1, y1, and z1, and B equal to x2, y2, and z2. Then the magnitude of V is, this time we're not assuming the initial point is the origin. So basically you have to do the subtraction of the components, then you take each differences to power 2. So the magnitude of V is going to be square root of quantity x squared minus y x1 to power 2 plus y squared. So let's talk a little bit more on 3D. Let's have vector V be the vector from point A to B. A is given by components x1, y1, and z1, and B is given by components x2, y2, and z2. Then remember, again, you want to use distance formula, but the initial point is not 0, 0, 0. Therefore, you have to find the difference between the components, then taken to power 2. So the magnitude of this V is going to be square root of x2 minus x1 to power 2 plus y2 minus y1 to power 2 plus z2 minus z1 to power 2, square root closed. This should look familiar. This is, again, the distance formula. Now I want to explain the distance formula a little bit. Let's look at the vector V, V sub x, or V sub y, and V sub z are the components given. Drop down a perpendicular to xy plane. Xy plane is right down here. from the point of intersection of that perpendicular, draw two perpendicular to x and y axis. Now, because you drop down the perpendicular to xy plane, this length is going to be from the end point of the vector to the point of intersection is going to have length v sub z. That's the z component of the vector. And because you drop these two perpendiculars, this length is going to be the x component of the vector. And that length, y component of the vector. Because this down here is a rectangle, then this side also is going to be the y component of the vector. I recommend looking at this a little bit deeper. Visualizing 3D is going to be an important part of the course. Therefore, it's good to start early. Now, the point is, I want to show you the distance formula. So I draw from the point of intersection, which turns out to be v sub x, v sub y, and 0. I draw a line to origin, and then I consider the highlighted triangle over here. Remember that we dropped the perpendicular to x-axis, so here it's a right angle, and that's the hypotenuse. Hypotenuse is going to be square root of v sub x to power 2 plus v sub y to power 2 quantity. Then from there, I want to consider another triangle. And this triangle, again, is a right triangle. One side is this big, this length. The other side is VZ. Another Pythagorean theorem, and you get that the length of the vector is square root of v sub x to power 2 plus v sub y to power 2 plus v sub z to power 2. Example, let V be presented by components 6, 3, and 2. Find the magnitude of this vector. Magnitude here is square root of 6 to power 2 plus 3 to power 2 plus 2 to power 2, which is 7.